Welcome to Fundamentals of Computers lecture series. This is the fourth session in which we will talk of CPU internals. Carrying forward from the previous session, in this session we will first discuss the internals of a computer and specifically internals of a CPU, and following that we will continue our discussion on CPU operations and instructions. The objective of this session is to get a better idea of what constitutes a central processing unit in a computer, where does it fit in the grand scheme of components and programming, and what is the relationship between the operations that a computer can perform and the instructions that can be executed on the computer and the CPU. As a quick set of reminders, we started this lecture series with the understanding of binary numbering system, and we saw why this numbering system is important for the computers. Next, we had a look of arithmetic and logical operations. We then saw how logical operations can be constructed using electronics circuits, specifically transistors. And finally, we had a look at how the logic circuits and in turn electronic circuits can be used to construct the arithmetic operations that the computer, which is one of the arithmetic operations, and we specifically saw the addition operation, which is one of the operations that the computer can perform. In this session, we will look at the computer components and role of those components with reference to programming. Keep in mind that a computer has a lot of components. All of them are significant, but our discussion is focused on the components that play a part as far as programming is concerned. With reference to programming, there are four major components. First one is the motherboard. This directly does not play a role in the programming, and the programmers do not see the motherboard playing any part in the programs that they write, but it connects all the components, and that is why it is mentioned, and it has its significance. The most important component with reference to programming is the central processing unit, where almost all operations that a computer can perform are residing and can be performed. I say almost because there are a lot of operations that are performed outside of the CPU, and as the computers become more sophisticated and more complex, a lot of operations are moved outside of the CPU, and the best example of that is a graphics processing unit, which actually performs all of the screen rendering and graphics related operations. Out of the three main components, CPU, RAM, and permanent storage or hard disk drive, the CPU performance wise is the fastest component of the three. It can perform the operations very fast compared to the RAM and hard drive. The second component that is of significance with reference to programming is RAM. RAM is significantly fast compared to a hard disk drive, but it is slower than the central processing unit. RAM is a non-persistent storage media, which means that anything that is written on the RAM, once the power is cut off or the computer is shut down, it is erased, and the next time you turn your computer on, new data and new information needs to be loaded into the RAM for that to be available to the user. What is stored on the RAM? We store instructions and data on which those instructions have to operate. The instructions are the software entity that is linked with the operations of the computer, and later on we will see how the instruction is related to a operation that the CPU can perform. The third significant component is hard disk drive. I have used the word hard disk drive here. However, any persistent storage media where the information can permanently be stored will be considered as the third component. Specifically, these days, solid state drives have roughly replaced the hard disk drives in almost all the computers. So any media where the information is permanently stored is referred to this third component, and this is the slowest of the three: CPU, RAM, and hard disk drive. The data and the instructions that are stored on the hard disk drive, they remain there permanently until and unless we intentionally, the user wants to delete that information. As far as speed is concerned, this is an important slide. If the purpose of this slide is that if RAM and hard disk drive, both of them store the instructions and data, why don't we just remove one of them and keep the second one? So the answer is that CPU is the fastest component. It's very, very fast. And to give you an example, when we say that this is our 2 gigahertz processor, which is a very slow processor to be very true, we are saying that this processor can do 2 into 10 raised to the power 9 different things. And by things, I mean different instructions in a single second. Okay, so that's a lot of different operations that a CPU can perform within a single second. RAM, on the other hand, is significantly slower compared to the CPU, and it is roughly about 50 times slower compared to a CPU. This is a ballpark kind of figure. The different type of RAMs will have different speed comparison compared to the CPU, but in general, the idea is that this is slow. So if CPU is performing an operation and it wants to get some instruction or some data from the RAM, it will take, the CPU will wait for 50 operations, 50 cycles before the data can be fetched from the RAM. So that's a lot of time wastage by the CPU, which is one of the precious resources of the computer. On the other hand, hard disk drive is even slower compared to the RAM. So it is slower compared to by a factor of 300 to 3000 times, and therefore if the CPU has to fetch the data directly from the hard drive, that will be very, very slow. And therefore we use an intermediate medium in the form of RAM, where the data is relatively lesser slower, and then other mechanisms, for example prefetching, are used to cover that slowness. So instead of just bringing in one instruction or one amount of data that needs to be used by the computer, it will by the CPU, it will bring in a lot of data at once, and then it will send the request for the next data from the RAM. Okay, so that way the speed problem can somehow be solved. The speed difference between the CPU and RAM, the problem that is caused because of that, that is somehow solved. Okay, so the main idea here is that the CPU must not wait for the hard disk drive or SSD drive, and for the same matter for the RAM, to complete its work before the next operation in the CPU can be performed. Now we will specifically look at the central processing unit, or CPU, which is the main component for our discussion today, through which we will go on to the CPU operations and instructions and the relationship between them. So I'm just going to give an overview. We will not really be talking of everything that exists in the central processing unit. So if you want to get more details, you can follow up with a very good computer architecture book, or you can wait for the lecture series that we will be doing on the computer architecture, where we will discuss the central processing unit in detail. As far as this session is concerned, it's an introductory session, and our objective is to reach to the programming as soon as possible. So we will only discuss the relevant details with reference to programming. So central processing unit is an entity that interacts with RAM. So a CPU has an interaction with the RAM shown over here. The CPU consists of a few components. One of the important components is arithmetic logic unit, or ALU. Arithmetic logic unit, or ALU, consists of data manipulation operations that can be performed by the CPU. So this is an electronic component. Okay, and those electronic circuits combined together perform the operations that are used for the data manipulation. For example, an addition operation, a subtraction operation, and so on. So those electronic circuits exist in this ALU. The second significant component of the computer is our CPU is the control unit. The control unit consists of control change operations that a CPU can perform. One of the control change operations is to actually change the order of operation of instructions. We will see this in the subsequent slides, but one of the operations that the control unit performs is to change the order in which the instructions are executed. Control unit is very closely coupled with the clock. Clock helps the compute. Clock is the ticking element which provides the events for the computers. We'll talk of that in a minute. The third important component of the computer is registers. Different computers have different number of registers in the CPU. Registers are like RAM storage media. However, registers are very fast. They are designed with the expensive technology that can cope up with the speed of the rest of the components of CPU, and they store or hold the data that is needed by the arithmetic logic unit to perform the operations. Next component is cache. The cache is divided into two parts. There is an instruction cache or I cache, and the second portion is the data cache. So all the instructions that are issued, the software instructions that are issued to the computer are stored in the I cache, whereas the data on which those instructions or operations are to be performed is stored in the D cache. This area is used for storing the instructions when those are prefetched. So suppose the computer is performing the operation number 10 right now. In the I cache, we can fetch. We know that after the 10, the next operation is going to be operation number 11, the next operation is going to be operation number 12, 13, 14, and so on. So we can prefetch those operations and store them in I cache. However, the I cache is very fast. Once again, it operates nearly at the speed of, not exactly at the speed of, but nearly at the speed of the CPU, rest of the components of the CPU, and therefore it is expensive technology, and we cannot have a lot of I cache in a processor. That will increase the cost of the CPU significantly, and it will become an unviable and very expensive device. So we can only store limited amount of instructions over here because of its size, and so those instructions are then fed into computer. There is another reason of why we cannot store a lot of instructions, because the control unit, depending upon the requirements of the program, can change the order of execution of instructions, and in that case we will need the instructions to be fetched that are not present in I cache. This is a portion that we will talk of when we will talk of operating system. So keep in mind that it's not viable to fetch almost all the instructions into I cache, even if a very large sized I cache is available. So is the case with the data. So they just provide the faster access to data and instructions compared to the RAM. MMU, or memory management unit, is the component that brings the data from RAM into the CPU, specifically to CPU cache, and it also stores the data back from CPU into the RAM. Clock is the event generator of the CPU. So CPU is an event-driven component. What does that mean? It means that the CPU cannot perform its operations on its own. Something else has to happen that will trigger the next operation of the CPU. And that something that will trigger the next operation is the clock. When the clock ticks, on every clock tick, the CPU performs one operation, okay, or one set of activities. The clock generally operates at the speed when we buy the computers. One of the things that is asked is the speed of the processor. So it's a 2 gigahertz processor, 2.6 gigahertz processor, and so on. So that 2 gigahertz means that this clock ticks for 2 into 10 raised to the power 9 times within a single second. So many different things can be performed by the CPU within a single second. Now, let's look at the CPU in terms of operations, because we started our discussion in the previous session with the operations that a computer can perform, and we had a look at one of the operations, which is the addition operation. So now let's have a look at what operations the CPU can perform and where do they exist and how the operations are executed. So as I just mentioned, we had a discussion on addition circuit. So let's have a look at where that addition circuit exists in our CPU. So this is the same diagram that we just saw. Here is the arithmetic logic unit. The adder circuit or addition circuit, which is one of the circuits that exists in the arithmetic logic unit, that in the CPU, that exists in the arithmetic unit. So how does the addition operation perform? We had seen that an addition circuit consists of x number of full adders, where x is the number of bits that we want to add. So here I have just created an example of addition of an 8-bit number into an 8-bit number. Generally, the computer's registers are 16 or 32 or 64-bit registers. So 64 different full adders will exist over here. Okay, and similarly, the register will be able to carry 32 or 64 bits. So how does this addition operation work? Within the ALU, we will connect one of the possible registers as input number 1 to the arithmetic logic unit. So for example, this B register. Next, we will connect another register where we have stored the data. So how do we figure out this is the register that needs to be connected? That is where the data on which the addition operation needs to be performed, that data resides. So register number 1 is connected, then register number 2 is connected with the adder circuit, and finally the register number 3, R3, is connected with the adder circuit. So once these connections are complete, they don't exist. This connection portion does not exist before the operation is performed. So these are one of the things that are done at the time of the clock tick. So one clock tick will allow the connection of the two input registers with the addition circuit. Once it is decided that addition is the operation that needs to be performed, the next clock tick will actually connect the output register with the addition circuit, and then there will be another clock tick which will actually perform the addition, bring the value from R1 and R2 and store it back into R3. Okay, so this operation will generally get performed in 3 ticks. Actually, there are more than 3 clock ticks that are required to perform this operation completely. So this is the adder circuit. We had seen that in session 3. If you don't recall, you can go back and have a look at session 3 and see how the addition circuit is created using the logic gates. So addition is just one operation that the computer can perform. What other operations are possible, and how do we know which register to connect with the specific circuit, and how do we know which operation to perform, and so on? All of those details will be covered in the next session. Similarly, how do we know what operation the CPU needs to be performing? Because all the different tasks that we can perform through general purpose computers, we can play video games, we can browse internet, we can play songs, we can edit our text files, and so on and so on. There are a lot of things that can be done by through a general purpose computer. All of those operations cannot be performed just through addition. So there are multiple operations that need to be performed to complete a complex task that the user wants to execute. So the CPU can actually perform different operations. How does it know which operation to perform and when. For this, the information that is where the software comes in, okay, and that is decided through software instructions and instruction flow. Okay, so it's a software instruction that tells the CPU which operation to perform, and the sequence of those instructions, which is called an instruction flow, that decides what's the next operation that is going to be performed and what's the next operation that is going to be performed, and so on. Okay, so in the next session we will talk of more details of instructions and flows and their relationship with the operations that a CPU can perform. So the next session is going to be a continuation of the existing session where we'll talk of computer operations and computer instructions and the relationship between the two. This brings us to the end of our existing session. Keep our Patreon link in mind if you or anybody who has benefited from our sessions wants to support our effort. Until next session, goodbye and thank you.